So we'll start with the basic architecture of the CNN. So how the convolution pooling and fully connected layers are assembled into one working pipeline that we'll see from this. So this is going to cover all the individual building blocks, the convolution operation itself, why it shares the parameters, why it's equivalent, how pooling controls that equivalence, and the various specialized variants engineers built for the specific situation. So in the next section, we'll see how the convolution, pooling, and fully connected layers are assembled together into one complete working CNN pipeline. So because the understanding each block individually is only half the picture, we also need to understand how and why they are arranged in that particular order. So let's move to the next slide and go into deep with this CNN pipeline, which is our end-to-end pipeline over here. This is a complete pipeline, fine. So we start with the input image, pass it through a convolution plus a ReLU layer that extracts the local features. Then a pooling layer that downsamples and adds the invariance. This pattern repeats, and another convolution plus ReLU layer learns deeper, more complex features, followed by another pooling layer that downsamples further. After the convolutional stages, we flatten everything into a one-dimensional vector, pass it through a fully connected layer that combines all extracted features, and finally, a softmax output layer that produces class probabilities. Now, let us understand why ReLU sits right after every convolution. Right? So, since we haven't explained that in the detail till now, so the convolution and on its own is a purely linear operation. It's just weighted sum. So if you stack 10 convolutional layers with no nonlinearity in between, mathematically entire stack would collapse into something equivalent to a single linear operation. So no matter how many layers you added, because a linear function of a linear function is still just a linear. So this would make depth completely pointless. Here comes the ReLU. So ReLU defined as the maximum of zero, and the input introduces nonlinearity by clipping all negative values to zero. And this simple operation is what allowed stack layers to represent genuinely complex nonlinear functions, which is essential for recognizing complex visual patterns. So the intuition behind why this whole pipeline works is important. Early layers learn simple things like edges, colors. The middle layer combine those into the parts like eyes or the wheels, and the deep layers combine those parts into the whole recognizable object. This happens naturally because each layer's receptive field is built from the receptive fields of the layer before it. A neuron in the layer 2 sees a small patch of layer 1's output, but the layer 1's output already summarizes information from a patch of the original image. So layer 2 neuron indirectly sees a larger patch of the original image than a layer 1 neuron does. So the stacked enough layers and the neuron deep inner network can indirectly see almost the entire image. So letting them represent the whole object concept, even though every individual filter is small. Now there is a one real limitation to flag here. So namely stacking many convolution and pooling layers on top of each other causes a problem called vanishing gradient. Again, I will repeat. So just stacking many convolution and pooling layers on top of each other, which it causes the vanishing gradients. As the network gets deeper. So here why this happens conceptually? Because during the training, the gradients are computed backward from the output layer to the input layer using the chain rule. So which means the gradient at earliest layer is the product of many gradients terms from all the layers after it. If each of these individual terms is somewhat less than one, multiplying many of them together makes the product shrink exponentially with the depth. So until the gradient reaching the earliest layers becomes so tiny that Those layers barely learn anything at all. So this was later solved by the ResNet skip connections, so which gives the gradients a more direct path backward through the network. So bypassing this repeated multiplication. So we won't cover the ResNet in detail now, but it is where this has been overcome. I hope this CNN pipeline end to end is clear with all of us. So, as we have seen, the limitation is also given over here. Now we'll move to the next part, that is the type of layers in the CNN network. Okay. So let's see these types of layers. So let's be precise about the different layer types, and we will find in the CNN. So the convolution layer extracts local features and has the learnable filter weights. The activation layer, typical the ReLU, adds non-linearity, so the network can learn complex patterns, as we have just discussed. Without this, depth would be mathematically meaningless. And it has no learnable parameters of its own. Since it's just a fixed mathematical function applied element-wise, the pooling layer downsamples and adds the local translation invariant. And again, it has no learnable parameters since it's applying a fixed rule like the take the maximum rather than the learn weights, right? I hope you have understood this. That is the convolution layer. So it extracts the local feature edges parts, and yes, the filter weights are applied. Then we have the activation layer. So adds non-linearity so that the network can learn the complex parameter. Then we have the pooling layers, right? So the pooling layer, as I said, the downsamples and adds the local translation invariance, and again has no learnable parameters since it's applying a fixed rule like take the maximum rather than learning it through the weights. Then we have the normalization layer. The next layer you can see over here. In the normalization layer, we have like a batch normalization. It stabilizes the speed up training and do have the learnable scale and shift parameters. So these appears in the architecture after the LXNet. The core idea is that as data flow through many layers, the distribution of activation values can drift or become unstable, which slows down and or the destabilizes training. So normalization layers recenter and rescale the activations at each layer to keep training stable. So with the small number of learnable parameters that let the network undo this normalization if it turns out not to be helpful for the specific layer. Fine. And then I have the fully connected layer. You can see over here, there is a fully connected layer also. So this fully connected layer combines all the extracted features into the final decision and has a large number of dense weights. So we will just see like how large it is in a moment, right? And a softmax output layer, you can see it, the next one, that is a softmax output layer. Now, what does this softmax output layer do? It converts the raw scores into the class probabilities, usually without any class parameter, extra parameters beyond the final fully connected layer. So softmax works by exponentiating each raw score and dividing by the sum of all exponentiated scores, which guarantees the outputs as all positive and the sum to exactly one. So they can be interpreted as the genuine probabilities across the possible classes. So these are all about my types of layers in the CNN. Now we'll move and see the working example of the counting parameter. Right? So let's move to this working example. So a small CNN for 32 by 32 by 3 input. Let's see like where does this all parameters go. So we have seen multiple layers and now see the parameters of this multiple layers too. Let's actually count the parameters in this small CNN to see where they go. So take 32 by 32 by 3 input, similar to that is CIFAR 10 images. A convolution layer with 16 filters of size 3 by 3 and padding 1 gives us an output of 32 by 32 by 16 using 448 parameters. Right? So that's my first layer. Then I have the max pooling layer with 2 by 2 window brings us to 16 by 16 by 16 with the 0 parameter. Then so what we say here, the pooling never has the learnable weights as we have discussed already. The second convolution layer with the 32 filters gives 16 by 16 by 32 using 4640, that is 4640 parameters. Then there is another max pooling brings us to 8 by 8 by 32, again zero parameters. So we flatten this into a vector of 2048 values. Then a fully connected layer takes us to 128 units, cost 2,62,272 parameters, and the final output layer to 10 classes cost 1,290 parameters. So adding it all up, we get approximately 2,68,650 total parameters, right? So you can see there is a box at the right. Please have a look at that box in the right, and we can notice that roughly 98% of these parameters sit inside that single fully connected layer. Even though the convolution layers are done, the actual feature learning works, and then we need to understand precisely why this imbalance happens. So the reason is a fully connected layer connects every input value to every output neuron. So its parameter count grows as the product of the input size and the output size. So in our case, 2048 times 128. A convolution layer, by contrast, has a parameter count that depends only on the filter size and the number of filters. So it's completely independent of how large the special dimensions of input are, thanks to the parameter size, of course. So this is precisely the mathematical reason why flattening a large feature map and feeding it into a dense layer is so parameter expensive. And that's why we will see the becomes a real serious problem in the AlexNet, which is the larger scale, right? So now we'll look at the next is like what each layer learns. So let's see that what this early layer do, middle layer do, and then the deep layers do. So to build the intuition for what's actually happening inside these layers. So the middle layer combines the early layer, the first one, the early layer learns edges, colors, and simple features, textures. Middle layer combines those into the corners, shapes, and object parts, like think eyes, wheels, or the handles. And a deep layer combines those parts into whole recognizable object, like a complete faces or cars. So this is not just a convenient story for us. It's been directly verified by researchers who visualize what individual filters in a trained scene respond to at each layer. And this hierarchical structure shows up consistently across different train networks and even different stages. So it makes sense once you think about it from an information building perspective. Right. So an age is genuinely the universal reusable building block. Almost every object in the world is made of edges and boundaries. So somewhere it's statistically efficient for the network to learn age detectors. So first, since they are useful for recognizing the thousands of different object categories. So once the network has edges, combining a few of them in the right spatial arrangement can represent the corner or a curve, and combining several corners and curves can represent an eye or the wheels, and so on upwards. So this hierarchical feature learns, building the complexity gradually layer by layer, where each layer's building block are combinations of the previous layer's building blocks, and is exactly like the SIFT or the HOG combined with the traditional classifier like SCBM. Because those older approaches used a single fixed layer of the feature description designed by human rather than a learned hierarchy that adapts to the whatever the data actually needs. So that is all about the CNN, and then we have seen the basic building block pipeline of CNN, the type of layers in CNN, the working example where we have the counting parameters, and then lastly we have seen what does each layer do. So that's all is about the CNN.